twice. So. Okay, so the first of these conditions was this. And the second of these conditions is this. Okay, now, when you look at these conditions, you have to understand that you can see that they involve two things. They involve the Mayer cost, and they also involve the boundary conditions. So if it turned out that one of the, remember I said that either these are true or the variation in x at that initial or final time is true, right? What you see here is if it turned out that the initial state were, say, fixed, then your boundary condition would reflect the fact that the initial state would be fixed. And if that was the case, then your variation would be 0. So there would be nothing you could gain out of applying this condition, because this condition involves derivatives with respect to the initial value of the state. If the initial value of the state is known, there's no more sensitivity information you can get by saying that I'm going to now apply this derivative condition too, because I know everything about the initial state, right? So there's absolutely no benefit to doing this. So what I'm going to do today is I wrote these down here because I want to do an example. Now it's kind of an example, but it's more like a sort of it's a little more than just an example, okay? So I want to do this with the following problem, which is the linear quadratic optimal control problem. Now, it's important, this problem is studied so much in the literature, and I'm not going to do like a whole course on this, but the main reason this problem is so important is because in control, when you're actually trying to do control, you typically are interested in what's called feedback. And feedback is because you want to design laws that allow you to be able to determine the control as a function of the state so that you can write things in a nice, compact, closed form, and you can use them in real systems that have sensors and actuators so that you can feed things in and you can stabilize systems and you can do all kinds of wonderful things, stability augmentation. That's not the purpose of what I'm doing here, okay? What I'm doing here is I'm going to show you the mathematics associated with this linear quadratic problem, which is the reason it's studied so much. Well, in my opinion, the reason it's studied so much. This may not be the reason. Somebody who does control theory might argue with me. But the reason it's studied so much is because it can actually be solved. This is a classic example in what I call, we can solve this problem, therefore that's what we do. All right? I mean, so it's not that problems are actually linear. There aren't very many systems that are linear. There aren't very many systems that have quadratic, where you'd have a quadratic cost function. But the point is that it's a good problem from a mathematical standpoint to understand, especially this concept over here, which is, so the problem is stated as follows, is we say minimize j, where j is equal to 1/2 x at tf sf x transpose at tf. I'll define all these things in just a minute. Plus 1/2 the integral from 0 to tf of x transpose qx plus u transpose ru dt, subject to the constraint x dot equals ax plus bu, and the initial condition x at 0 is equal to x0. Okay, there's no constraint on the final state. Now, there are certain things that need to be met in this problem. When the classic assumptions in this problem, there are the strong assumptions and the weak assumptions. So for simplicity, I'll just do it with the strong assumptions because it's a little bit easier. So we assume the following. Q is positive semi-definite. R is positive definite. Those are the two on these two matrices here. And then we also say that the pair A, B is controllable. And the pair A, Q is observable. Now, some formulations of this, what they do is we assume that these are both symmetric matrices. So they're equal to their transposes. And by assuming that AQ is observable, it turns out that if this is positive semi-definite, that you can write Q as a product of two matrices, C transpose, and you can say AC is observable. It's the same thing, right? But because the rank of AQ is not going to be any different from the rank of AC if C is a factorization, comes from a factorization of Q. So these are the standard assumptions that are made. Now, why are these assumptions made? First one is this. If you look at this integral, you'll see that if Q is not positive semi-definite, then there's no way to guarantee that this term is necessarily going to be positive. It could be negative, right? Because the definition of positive semi-definiteness is if I take a matrix Q and it's positive semi-definite, then V transpose QV has to be greater than or equal to 0 for all V, right? So there's no way that you can guarantee that this thing's going to be positive if Q is not positive semi-definite. So that's why that's in there. The reason that R is chosen to be positive definite is because if it's not, or worst yet, if it's not invertible, then you wind up with an undefined feedback law, as we'll actually see when we get through all this stuff. So that's why that assumption is in there. The reason that the pair AB is said to be controllable is because if it's not controllable, then you can't guarantee that the roots of this closed-loop system are necessarily going to be in the left half plane and the system's going to be stable. So you have to have AB controllable. And the reason that this is taken to be observable is because if it's not observable, then you cannot guarantee that every single state is going to wind up showing up in the cost, and every single state has to wind up showing up in the cost. Otherwise, you may have a state that has no cost associated with it, or some linear combination of states that have no cost associated with them. So that's why that assumption is in there. So these assumptions are all there for a reason. So now let's just go through the optimality conditions for this problem. This is a nice, basic, standard problem. It doesn't have any fancy schmancy stuff going on in it. It's a quadratic cost functional with a linear dynamical system constraint. It's a nice problem to see how optimality conditions play out in when you get to a more complicated problem, you can't do it this way, but at least you have a baseline to be able to do it. So the first thing that you have to do in these problems is you have to form the Hamiltonian. That's the first step, right? So we write down the Hamiltonian. So we form the Hamiltonian. And the reason we form the Hamiltonian is because we need the costate equation. So we have to have the Hamiltonian in order to get that. The Hamiltonian is equal to L plus lambda transpose F. So in this case, we have that the Hamiltonian is equal to 1/2 X transpose QX plus U transpose RU, because that's L, plus lambda transpose times AX plus BU. Okay? That makes sense to everybody? Now, we need the following things. We need conditions. We need the costate equations, so the costate differential equations, and a condition in order to determine the optimal control. So the first of these is that lambda dot is equal to minus hx transpose. What I mean by hx transpose is the derivative of the Hamiltonian with respect to the rate transpose, right? This is a shorthand for minus the partial of h with respect to x transpose. I just write it that way instead. Okay? So let's look at this. What is dh dx? So the partial of h with respect to x is equal to the partial of h with respect to x here. So you got 1/2 x transpose qx. So the derivative with respect to x of x transpose qx is x transpose q. Derivative in this term, the only thing that's in there is a lambda transpose. So you got a plus lambda transpose A. So this says that lambda dot has to equal what? Minus this whole thing transpose. But Q is symmetric, right? So you get Q times X, right, minus A transpose times lambda. I didn't say A was symmetric. I just said Q was symmetric. So now we still haven't figured out what the optimal control is. Now, we assume that the optimal control, since the control is unbounded, the control has no limits. So that means that there's no bounds on the control, which means that whatever the control can be anything, which means the optimal control has to lie in the interior of the set, but the interior set is plus or minus infinity. It can be anywhere, right? So it has to be the case that the derivative with respect to the control of the Hamiltonian has to be 0, because that's only applicable in the case where you have a control that lies on the interior of the control set. I got through saying that last lecture. So if we take HU, this is the same thing as saying partial H, partial U. All right? So what is the partial of H with respect to U? What is that? We'll take the derivative here. Same thing. You take the derivative with respect to U here. You get U transpose R, and then you get plus lambda transpose B, and that has to equal 0. So what this tells me is if I solve this well, if I rearrange it, I get R, if I take the transpose of the whole thing, I get RU is equal to minus B transpose times lambda. Now, I said that R was positive definite, right? So it's invertible. So R is positive definite, which says that U has to equal minus R inverse times B transpose times lambda. So that's the optimal control. So now, if you look at that, you can substitute that control into the state equation, and what you get is you get x dot is equal to ax, and now you just substitute in for lambda, so you get minus b r inverse b transpose times lambda, which gives you, well, that's it, that's all you can do with that. So we'll write this in vector form in just a second. So the equations that I've got now, I've got x dot is equal to ax minus b r inverse b transpose times lambda, and I've got lambda dot is equal to what? Over here, minus qx minus a transpose times lambda. So if you write this in vector form, single vector form, you get a minus b r inverse b transpose minus q and minus a transpose. The whole thing gets multiplied by x and lambda. So that gives me a system of 2n first-order differential equations, right? There are 2n equations in here. The dimension of the state is n. The dimension of the costate is also n. So this is a system of 2n first-order differential equations, and they're linear. Now, just for simplicity, I didn't write this assumption up here, but let's just do this just because it gets more complicated if you don't, which is let's assume all these matrices are constant, okay? A, B, Q, and R are all constant because it makes the analysis a lot easier to deal with. Otherwise, the solution is a little more complicated if it's not. But assuming that they're all constant, what do we know the solution to this thing is? Well, let's just make a couple of substitutions just to see this. So suppose you say let P equal x lambda, and also let's just say that F is equal to A minus B R inverse B transpose minus Q and minus A transpose. Okay? So then we have a system that looks like this. Okay, where F is a constant matrix because all of those matrices are constant. Now, does anyone know the solution to this? You should all know the solution to this. If you don't, then it calls into question whether you should be in this class because this class requires some knowledge of linear differential equations, and I can't teach all that in this class. So what's the solution to this? Does anyone know the solution to this? If the answer to the question is nobody knows the solution to this, then we should probably either do a review or I should make all of you go home and do a review. So does anyone have any clue what the solution to this is? Has anyone seen this before? Yes, what's the solution to this equation? There's a concept I'm trying to get at here, but I can't get at it unless you understand what the solution to this thing is.
A 2-point boundary.
No. I want to know what the general solution of this differential equation is. I'm not asking you about optimal control. I'm asking you about that differential equation. What's that? What is it?
P of 0 e to the negative f.
P of t is equal to what? You can't just write this in any order. These are matrix equations.
Yeah.
What is it?
Matrix exponential.
The matrix exponential of what?
F.
Of f. What is the matrix exponential of f? What is that? Tell me what it is. E to the ft times p at 0. Everyone knows what the matrix exponential is, right? Okay. So now look at this, okay? So what do I need in order to solve this equation? I need P0. What is P0? P0 is equal to x at 0 and lambda at 0, right? Because I defined P to be x lambda, right? So tell me what they are. So what's x at 0? What's that? It's x naught. It's given, right? What's lambda at 0? Do you know what lambda at 0 is? No, we don't know what lambda at 0 is, so we got a problem. So, can we get lambda at 0? How are we going to do that? Okay, the optimality condition from what? We know what boundary condition on lambda? What boundary condition do we know?
We have to use one of the other conditions that we given.
Well, let's go through it. That's why I kept those on the board over there, okay? Because I need them, right? I didn't just write them on the board and leave them there for no reason, right? So I need to get these. So we need conditions on lambda, right? If we don't have conditions on lambda, we can't do this. We don't have enough information to be able to solve this problem. So let's start with the first condition. Lambda transpose at 0 is equal to what? It's equal to the partial of phi with respect to x at 0 minus nu transpose, plus nu transpose, there's a minus sign here, times the partial of phi with respect to x at 0. So what's phi? I'm not asking you to compute the derivatives. I'm asking you what phi is. It's 1/2 x transpose at tf sf times xf. Is this a function of x at 0? No. So the partial of phi with respect to x at 0 is 0, right? Okay, that's the first part. little phi. What's that equal to? It is. There are no boundary conditions. So I have a problem with no boundary conditions. So the problem statement is go from anywhere you want to go to anywhere you want to go to and minimize this cost function. Is that a sensible problem statement? Not a sensible problem statement. There have to be some boundary conditions. What are they? By the way, they're on the board. There we go. X at 0 minus x0 has to equal 0. Right? Just because it's simple doesn't mean it's not a boundary condition, right? This last thing I knew, simplicity didn't mean that it wasn't there, right? It's still there, right? So what's the partial of phi with respect to x at 0? Please don't say 1. The identity, right? Okay? So what this says is it says lambda transpose at 0 is equal to what? Well, this thing is 0, so I don't need to worry about it. Plus is nu transpose times what? The partial of phi with respect to x0, which is the identity, which is just equal to nu transpose, which says that lambda at 0 is equal to nu. What does this tell me? Well, what does it tell me? Tell you anything? What's new? It's the Lagrange multiplier of the boundary conditions, right? Yes? Do I know what this is? Do I know what nu is? No, I don't know what nu is, right? So this says that lambda 0 is equal to nu. I don't know what nu is. So do I know what lambda 0 is? No, because it's equal to something I don't know, right? So this says something I don't know is equal to something else that I don't know, right? So this is a completely useless equation because I don't know any of this stuff, right? So if you tell me that I've got a number out there in space and it's equal to some other number, but I don't know what that other number is, how in the world am I supposed to know what the first number is, right? Because it's equal to something else I don't know, right? That's exactly what this condition is. This condition is absolutely useless, right? There's no information I gain from this condition. And that's the way it should be because I know the initial state. And you see, I don't know anything about the initial costate. So the fact is, if I know the initial state completely, I will get no information from the transversality conditions on the initial costate. And I shouldn't, because there's nothing in here that's imparted that's going to allow me to do anything that I couldn't already do because I already know what the initial state is, right? So the sensitivity doesn't help me one bit at the initial point. Now let's go to the final point. Okay, the final point, I have some other things going on here. I know that lambda transpose at TF is equal to the partial of phi with respect to x at TF minus nu transpose times the partial of little phi with respect to x at TF. What's the partial of big phi with respect to x at TF? There's phi right there. If I take its derivative with respect to x at TF, what do I get? I get x transpose at TF times SF. By the way, I have to know what SF is because I have to know what my cost is, right? So SF is a known quantity. So this I get. What's this over here? What's this term? 0, right? Because phi is only a function of the initial state. It's not a function of the final state, right? So this term over here is 0. So that means that lambda at TF is equal to what? It's equal to SF, which is, again, assumed to be symmetric, times x at TF. Now, I don't know what the final state is, right? Just like I don't know this over here. The difference is, though, that I have something that will allow me to be able to determine what the final state is, namely this system of differential equations over here. In this case here, I had nothing that would help me determine anything. It was just a single isolated equation that had nothing to do with the rest of the problem, right? So now, if I add these boundary conditions into the problem statement, I'm going to go back and use x again. I've got x dot lambda dot is equal to A minus B R inverse B transpose minus Q minus A transpose times x lambda. But now I have the boundary conditions that x at 0 is equal to x0 and lambda at TF is equal to SF times x at TF. Now, how many boundary conditions do I have? 2. How many? How many boundary conditions do I have? When I say how many boundary conditions, how many scalar boundary conditions do I have? I have 2n, right? Because I have n boundary conditions here and n boundary conditions here. So now, in principle, I can solve this, right? Because I have the right number of boundary conditions. If I have a system of 2n differential equations, I need 2n boundary conditions in order to solve it. But I have a bit of a problem here. What's my problem? N of them are at one endpoint, and the other end are at the other endpoint, right? So I have what's classically known here as a 2-point boundary value problem. This is a 2-point boundary value problem. Problem with it is exactly that. It's a 2-point boundary value problem. It's not a boundary value problem where you can just integrate from one end to the other. I mean, you've got information missing at either end. So how are you going to solve this? I mean, you know the solution looks like this, but how are you going to solve it? All right, so in the linear quadratic problem, what they do is, and some people think that this is like algebraic gymnastics, but it actually has a solid basis in theory. So it's not, is that we know that because this is a linear system, that the solution to the differential equation is unique. It's only true for a linear system. Linear systems have unique solutions. That's the only solution to that equation. So as long as I find a way of being able to generate a solution that gives me that when I'm all done, I know it's the solution. There is no other solution. So it doesn't matter what algebraic gymnastics I do. As long as I do them in such a way that I wind up with that solution, that's the solution. Okay, so what we do is we identify it this way. We say, suppose we let lambda equal, I'm going to call it S times x plus beta. Now, you say, well, what does that do for me? And I say, okay, well, I haven't lost any generality in this. And the reason I haven't lost any generality is because if I make this a little more explicit and I put the dependence in here on t, what I'm saying is that lambda of t can be any function beta, which I don't know what beta is at this point. It can be any function beta plus this thing sx. So as long as this function is unconstrained over here, I haven't lost any generality because I'm replacing one general function with some other general function, except for the fact that I'm just allowing for it to have this additional term in here. But beta can be anything, so it doesn't make any difference. So now, suppose I take the derivative of this. What's lambda dot? Well, I'm assuming also that this is a function of time. It's not a constant. Okay? So if I take the derivative, I get s dot x plus s times x dot plus beta dot. What's x dot equal to? What's x dot equal to? It's equal to a x minus b r inverse b transpose times lambda, right? And then I got plus beta dot. So if I rewrite this, what do I get? I get s dot plus sa, this whole thing times x, minus sb r inverse b transpose times lambda plus beta dot. Well, what's lambda equal to? lambda equal to? It's equal to Sx plus beta, right? And then I get plus beta dot. Yeah? That okay with everybody? So let's keep going with this. I can erase these now. So I've got lambda dot is equal to, I'm gonna put it over here because I don't want to keep looking over there. Okay. Let's look at this for a second. Now, if you look at this, you can see that if you look back at the original equation, right? If I now write in what lambda dot is, what's lambda dot equal to? Lambda dot is equal to minus qx minus A transpose times lambda, right? And that has to equal S dot plus SA minus S B R inverse B transpose, the whole thing times X, minus S B R inverse B transpose times beta plus beta dot. But I know that lambda is equal to Sx plus beta. And that has to now equal S dot plus SA minus SB R inverse B transpose, the whole thing times X, and then minus SB R inverse B transpose times beta plus beta dot. So now let's solve that whole thing for beta dot. And let's see what we get. If I solve it for beta dot, I get that beta dot is then equal to, so I just take everything else to the other side. So I've got a minus qx minus S transpose A. So they stay there. And then all this stuff winds up going to the other side. So I wind up getting minus S dot, and I get minus SA minus A transpose S plus SB R inverse B transpose minus Q, the whole thing times X. That takes care of everything here. And that has to, and now what else do I get? I get plus, and now I have to take all the terms that involve beta. So beta, if I take this to the other side, what do I get? I get A transpose minus SB R inverse B transpose, the whole thing times beta. Okay? Now, if you look at the equations now, you can see that what I've done is I've replaced lambda with this new function beta. So beta is now just as general as lambda was. There's nothing, I haven't restricted it in any way. I just said whatever this function is, I'm going to stick it in there, and I'm going to let lambda equal Sx plus beta, and now I'm going to go through the formalization or the formulation with beta instead. So suppose we do this. So we're going to say I'm going to say gamma of S equal minus S dot minus SA minus A transpose S plus SB R inverse B transpose S minus Q. So if I do that, what we get is we get X dot is going to equal, and beta dot, let's write all this down, and beta dot together are going to give me this system. Well, X dot is equal to A, and I've got, actually, let me do the full substitution on X dot first, too. So X dot is equal to A minus B R inverse B transpose times Sx plus beta, which gives me A minus B R inverse B transpose S times X minus B R inverse B transpose times beta. So now if you take that whole thing and you do the subs and you put it together in one single matrix equation, you get X dot and beta dot together are equal to A minus B R inverse B transpose S. And you've got, in this corner over here, with the beta, you've got, this is a minus, right? Yeah, that's why I made the mistake. Yeah, it takes it to the other side. Minus A transpose plus. A plus, right? No, it's a minus. No, it's minus. Hang on a second. It's minus A transpose beta, so that's correct. And then I take this to the other side to get a plus. Okay, right. Okay, that's fine. I'll rewrite it over here. So I've got SB R inverse B transpose minus A transpose. I've got gamma of S, and here I get minus B R inverse B transpose times X lambda. Okay? Now, by doing that whole algebraic manipulation, it seems like we haven't done anything. But what we've done is as follows, is that when we did this substitution, we didn't specify anything about what this function beta was. We said that beta could be anything, and I also didn't tell you anything about this function, this matrix S. I said S could be anything. So what we know, though, is that if I find a solution to this problem, it has to be the only solution to the problem. So what we do is it says, right now, S has not been chosen or has not been specified. So we choose S to satisfy the following condition, which is gamma of S has to equal 0. If gamma of S has to equal 0, it says that that whole term in there has to equal 0, which says that S dot has to equal minus SA minus A transpose S plus SB R inverse B transpose S minus Q. Now this equation right here is called the Riccati differential equation. Riccati differential equation. But in order to solve it, we need a boundary condition, right? We need some condition on this. It's a differential equation. It can't solve it without an initial condition. So the way we get the equation is as follows. Is that if you look at this system right here, if this is 0, right, if I say that S is 0, S satisfies this equation, so gamma of S is 0, what I get is I get beta dot is then equal to SB R inverse B transpose minus A transpose times beta, because this thing is 0. Which means that beta is no longer coupled, this is a beta, sorry. Which means that beta is no longer coupled with X. It's its own differential equation, right? It's been decoupled from the rest of the problem. So if you look at this right here, you say, well, what's the solution to this? Well, I know that lambda is equal to Sx plus beta. But we also know that lambda at Tf is equal to S at Tf times X at Tf, right? Because that was the boundary condition that I got when I derived the optimality conditions, right? So if this has to be true, what this says is it says that beta at Tf has to equal 0. It's the only way, right? Because if I put this back in here, since these two things cancel each other out, beta at Tf by definition has to equal 0 at that point, right? If beta at Tf has to equal 0, what kind of differential equation is this? What kind of differential equation is it? Assuming you know what S is. Assume you've solved for S in this equation. What kind of equation is this? It's a first order linear differential equation. It's not a constant coefficient differential equation because S changes with time, right? But it's a first order equation and it's linear, right? Because I know what this matrix is. So this is beta times beta dot is equal to something times beta. So because of that, since this is a linear differential equation and it has a boundary condition that at some value it's equal to 0, the solution is that beta of t has to be identically 0. That's the only solution to this problem because it can only have one solution, right? That differential equation can only have one solution. And if its value is 0 anywhere, it's going to be 0 everywhere. There's no way it can be anything else, all right? And the reason is because this is equal to the transition matrix times whatever that condition is, but it doesn't matter what the transition matrix is. That condition is 0, so the solution is identically 0. So this means that this thing is identically 0. Well, if beta is identically 0, what that says is it says that the solution to this problem now can be obtained from the following, which is that we take the Riccati differential equation. So the Riccati differential equation is this thing over here. So the Riccati differential equation bless you, has a final condition that S at TF has to equal SF, which is the value I put in my cost, right? So you can integrate it from TF back to T0, and this will generate for you S of T on 0 to TF. Now, once you've got S of T on 0 to TF, now you have everything you need to solve this problem, which is that you know that X of T, or X dot of T, is equal to A minus B R inverse B transpose times X, right? And we know that X at 0 is equal to X0. S. And we know S. From solution of the Riccati equation. But you see, this problem is a great problem to understand a bunch of different things. I went through the whole solution with you because I know everyone likes to see the whole solution. But it's not really the solution that matters. The solution's interesting. It's got all kinds of cool stuff associated with it. If you're taking a course on linear control and you're going to learn linear quadratic control, this is a very interesting problem. There's no question about it. But when you look at the original problem and you write down the optimality conditions, you see that you run into this conundrum that you don't have a full set of boundary conditions at either end. So this is one of the classic things that when you look in papers on optimal control that people wrote 20, 30 years ago, I mean, honestly, people would get papers out of, I figured out a way to get the final costate, for some component of the costate at the endpoint. And that made it possible for me to integrate this equation backward from the final time and be able to do all kinds of these other things. And these were big deals back then, right? I got the final costate. I didn't know I could do that, right? And that became like a big, big thing. This problem right here is kind of the first problem where you're able to do that. You're able to decouple the system into a different form so that you actually don't even have to worry about the costate. You worry about this other function beta, and it turns out that the way in which the boundary condition was specified, it got rid of beta entirely from the problem. You see that when you're all done, beta disappears because its solution is 0, right? Because it has a terminal condition that it's equal to 0 because of the manner in which I define the transformation from lambda to beta, right? So what you get is this like sort of decoupling nature of being able to get terminal costates and being able to say, okay, I got that value of the costate. Now I can do some integration and I can simplify this equation down and I can analytically solve. It was a very, very big deal in optimal control for many decades. Now people just beat the crap out of these things with computers. But back then they couldn't do that, right? Think about it this way. Okay, imagine you're sitting in the year 1976, all right? It's hard for a lot of people. It's hard for me too because I wasn't in college in 1976, all right? And you don't have a computer. You guys are so lucky. You guys have it good. You can just fire up MATLAB, right? There was no MATLAB in 1976. You didn't even have as good a computer as you have on one of these, right? This is a great computer compared to what you had in 1976. Could you solve these optimal control problems with your iPhone? For those of you who have an iPhone? Probably not, right? Now imagine I took your iPhone away from you, and all you got is pencil and paper. And you got a slide rule, right? That's what they used back then. They used slide rules, right? This is how they did calculations. Imagine this is all you had. You guys, most of you would be absolutely roasted. You wouldn't know what to do because you don't have the tools to do it because you haven't been taught that way. You've been taught, well, I just fire up MATLAB, right? Well, that's not the solution to the problem. These guys had real problems on their hands. You know, imagine that even when you had a computer, it was this giant machine that would take up a room that was 6 times the size and volume of this thing right here, and it had this huge cooling system that would run through it all day long, and you had to pay hundreds of dollars an hour in order to be able to run your job, and you had to run it all through with key punch cards and all this stuff. Imagine what life would have been like. You would have gotten things done very slowly, right? And you know, the rates went down at midnight, so if you were going to run your job at midnight, it would only cost you $50 instead of $100, and you had an account, and once you ran out of money, the computer operator would say, too bad, you're out of money, you can't run your job. And worse yet, you made a typographical error when you were putting your punch cards together, and you had to run the whole job again from the beginning because there's no way you can run through punch cards and just fix the typo. Nope, you got to take the whole deck of cards, and then people used to do this. They used to walk around with these big boxes of cards, you know, these key punch cards. And this is what they do. Each card contained a character, contained a line of code with a bunch of characters that you would punch out what was on that line. And you were confined to 72 characters. The line couldn't be any longer than 72 characters. And it couldn't take up the first seven text columns. It had to start in column 8 or column 7 or column 8, one of the two. And it could only do 72, so the whole width was 80. That was it. That's all you had was 80 total width. And if you made a mistake, you had to run the whole job, each card, through the computer again. And you weren't doing this. Your computer operator was doing this for you at midnight when the rates were cheap, because that's how things work. So now you can see that this is actually a big deal. If you're sitting in that situation, you're like, I really want to solve this thing analytically because I don't want to have to deal with that, right? That wasn't an easy thing to do back then. So these were not simple things. So when you look at this and you say, oh, it's a bunch of mathematical mumbo-jumbo, put yourself back in a time period when really nobody had computational power. And even now, you have computational power. What happens is you just wind up running, well, the computer says. The computer doesn't say anything. You say it because you told the computer what to do. So there's no such thing as the computer said this. This is what I told the computer to do, and this is what I got. That's a good answer, right? Not the computer said this, right? Last thing I knew, computers weren't people, right? They can't talk. They just do what you tell them to do, all right? So we'll pick this up on Friday.